The human body, a perfect machine, full of wonder, a self-regulating system able to repair itself when injured and defend itself from viruses and illnesses. Yet, in this amazing vehicle, which we mostly take for granted, sometimes things can go wrong. A prime example is cancer, the disease of our century. Each individual responds in different ways to medication, and we're naturally frustrated with the one-size-fits-all approach, because often the more complex the disease, the more personalized the treatment needs to be.
I've been diagnosed with this disease. A large mass around 20 centimeters has been found in my liver.
I've been diagnosed with colorectal cancer.
Over 1.5 million men and women will be diagnosed with cancer this year in the USA, and more than 500,000 will die of it.
If the purpose of life is to reproduce itself, then the paradox is that cancer is actually very, very successful. It is the dark twin of life.
Cancer is not one disease, but many diseases with many causes. But there is one fundamental feature common to all cancers: the abnormal growth of its cells.
Most cells can only replicate a finite number of times. Cancer cells can just go on dividing forever, basically.
We tend to consider cancer as a modern illness, but most likely the first witness of this disease was an Egyptian doctor, Imhotep, who described what we know as breast cancer today. This was the only disease among the 45 he described for which no therapy was suggested. The word cancer was introduced by the Greek doctor Hippocrates, who observed that the morphology of some of these diseases looks like a crab, or karkinos in ancient Greek. At the end of the 19th century, two historical breakthroughs in fundamental physics marked a turning point for progress in cancer diagnosis and cure: the discovery of X-rays in 1895 and the discovery of radioactivity in 1898.
X-rays were the quickest example in history of a transfer of a physics discovery to a medical application.
The same happened with radioactivity only 3 years later. December 1898. Marie and her husband Pierre Curie, along with Henry Becquerel, discovered a new phenomenon in some minerals containing uranium salts. These elements emitted a mysterious radiation that left tracks on photographic film. They found natural radioactivity, a property of some nuclei which transform into different nuclei because of an excess of protons and neutrons emitting particles in the process. Radioactivity and X-rays open up an entirely new field of physics, the physics of the atomic nucleus. They were the first in a sequence of revolutionary discoveries often awarded with the Nobel Prize, starting a fortunate synergy between physics and medicine.
Medicine today is still benefiting from the continuous progress in nuclear physics, both in diagnostics and therapy. Among the most recent developments, PET, positron emission tomography, is the result of two scientific breakthroughs: the discovery of antimatter and the invention of cyclotrons.
The letter P in PET stands for positron, the antimatter equivalent of the electron, the first antimatter particle theorized by Paul Dirac and discovered by Carl Anderson. Another physics discovery was necessary for the invention of PET, the cyclotron, by Ernest Lawrence in 1930.
Behind this door we find the cyclotron, a particle accelerator that allows you to produce F-18 starting from the oxygen contained in water. And here is the cyclotron in a vertical position.
The protons produced in the center of the cyclotron are then accelerated 120 times. Once extracted, they hit a target containing water enriched with oxygen-18. When the protons hit water, oxygen-18 is transformed into fluorine-18, a new isotope. Fluorine-18 is extracted from the cyclotron and taken to the lab, where it is attached to a sugar molecule. This compound is called fluorodeoxyglucose, or FDG, and is the most used contrast element in PET. Compounds like FDG must be used for imaging within about 10 hours because half of the unstable fluorine-18 atoms reverts to oxygen-18 during the first 2 hours. And then again, the process is repeated until all unstable fluorine-18 atoms have transformed back to oxygen-18. The compound is injected into the patient. Cancer or any inflammatory cells are hyperactive and greedy for sugar, so they absorb FDG very easily. After injection, the patient rests for some time to let the radiopharmaceutical accumulate. Used nowadays are peptides, small chains of amino acids with the ability to enter cells. Peptides are equipped with a chelator. That's a sort of hook capable of catching an unstable atom such as lutetium-177. When it becomes stable, lutetium-177 has the property of emitting 2 types of radiation at the same time: a gamma ray, which is used to make SPECT images, and a beta particle, an energetic electron which travels a few millimeters into the body, releasing energy. And that is the killing agent used to destroy the tumor, to any tumors in the body. If the tumor cells express the right receptors, they attract the peptide like strong magnets, so the peptide can fix onto the cells. Once inside the tumor cells, the peptides emit both gamma rays and electrons at the same time, and the tumor mass begins to squeeze down until all the cells die. Billions of these small events per second in a few days are enough.
Nuclear medicine for therapy is not yet a routine practice because the drugs have not yet been registered. Particularly because there aren't enough doctors specialized in nuclear medicine. But I'm optimistic for the future because we're having excellent results with this therapy. Since they don't affect the entire body, but only target 6 cells, these drugs don't have any side effects, and I can go about my life as usual.
Focused and personalized approach to the treatment of complex, incurable diseases like cancer. Targeting the cure should not only lead to better health, but it can also lead to wealth. By integrating diagnostics and therapy, molecular nuclear medicine is shaping a new age of patient care. The age of personalized medicine.